Do example 2. Remember last week we saw when I was doing the theory section, we were using this equation, and we saw that if you assume that the density of the Earth's atmosphere is constant, then the pressure at the top of a mountain that is about 2,000 meters high is going to be 0.75 atmospheres, so roughly about 0.75. So let's say the mountain is like this high. The atmosphere is 1 atmosphere. Here it would be 0.75 atmosphere. But in reality, the density of the Earth, as you go up, the density of the Earth's atmosphere is decreasing. So the density as a function of height is equal to, the function can be approximated by this function, 1.29 e to the minus h over 8,000. By the time that you reach a height of about 700 kilometers, so this one I'm assuming is, let's say, 2,000 meters, which is 2 kilometers. By the time you reach roughly about 700 kilometers, the density is approximately 0, and you have already reached what's known as the exosphere, the outermost layer of the atmosphere, which is very, very thin, a very thin atmosphere. Up here, we're going to say if you have a column of air, if I know the pressure here at the bottom, the P bottom, so if the P of the bottom is known and I want to know P at the top, the difference of those pressures, right, delta P, is given by rho G and the height, right? The P at the top is bigger by that much, rho GH. But the pressure, this is a differential now. You have the pressure is going to be dP, rho is going to be 1.29 e to the minus h over 8,000, then G, and then this is going to be dH, because I'm going to take an infinitesimal height, dH, and I'm going to say as the height is small, the density is given by this function, and now I'm going to integrate this. Integrate. Let's see what happens here. So basically, I derive this from this equation. If you subtract this, you get delta P is rho GH. Okay, so here I integrate this from pressure of the atmosphere to the pressure of the top. So I get pressure top minus pressure atmosphere is equal to the integral of that. The integral of e to anything is itself. So we're just, the number here and the number there is going to come out in the front as a reciprocal. So I'm going to get is equal to negative 1.29 times 8,000. Right? And now I'm going to integrate this from 0 to 2,000. So my so now I have 1.29. The negative of the 8,000 came outside, and then I have G, which is 9.8. Okay, and I'm assuming G is constant for the height that we're talking about, the height ranges, and the integral of that is just going to be e to the minus h over 8,000 from 0 to 2,000. Okay. And so now I'm going to have pressure at the top minus the pressure of the atmosphere, 1.013 times 10 to the 5th is equal to, and then over here I get basically, let's multiply this, you get 1.29 times 8,000 times 9.8, So I get negative 101136, and then over there I get e to the negative 2000 over 8000 is 0 zeros canceled, so it's just 2 over 8 minus e to the 0, which is just 1. And then this negative switches the order, so you basically get pressure at the top is equal to 1.013 times 10 to the 5th. And then this thing switches the order of that, so you get plus 101136, 1 minus e to the minus 1/4. Okay? So you get 1 minus e to the negative 0.25 power. Okay, so 1 minus e to the power negative, you could say power quarter. Okay, times 101136. Okay, so I multiplied it by that, and this number comes out to be 22,371.20. Then I add that to 1.013 times 10 to the power 5. I get 123,000. Now I purposefully made a sign mistake here to illustrate something. You have to be careful when you are setting this integral up. Okay, so remember when I first set it up, I said if we have a column of air, and I said P at the bottom is equal to P at the top, okay, and plus rho GH. Then I took this over there and I called this delta P, and then I called this delta DH, and I integrated it. So I wasn't really careful about the minus signs. I just went, you know, okay, delta P, rho GH, and da-da-da-da-da. I integrated it, and I'm getting a pressure at the top which is greater than atmospheric pressure. Well, that can't be. As you go up, the pressure should decrease. Well, that mistake was on purpose to show you, you have to be careful here. When you subtract P top, when the P top goes to the left, right, you end up with P bottom minus P top, which is actually inverse of delta P, which is actually negative delta P, rho G dH. Okay? So the equation should be dP is negative rho G dH. So the differential equation should be dP is negative rho G dH, not dP is rho G dH. Because what happens is as the height goes up, the pressure decreases. So the pressure, the dP should be negative. Okay. dP is equal to negative rho G dH is the correct version, not dP is equal to rho G dH. Because as the height increases, the pressure should decrease, right? So if I do that correctly, then what would have changed? Well, I would have had another negative sign here, which means this sign would have stayed. If I had another negative sign, that would have been positive, positive, and then this would have come out to be negative, negative. So this would subtract from that. So that is the correct answer. And I would end up with 1.013. So it's not a big, big difference, but it's still different. So the answer comes out to be 0.78 atmosphere, whereas when we assumed that the density was constant, the pressure was 0.75 atmosphere. So as you go more up even, the difference in the answers will become more bigger, you know. So if you go to 6,000 meters, 10,000 meters and stuff, the pressure will not drop as quickly. That's why it takes all the way to 700 kilometers before the pressure has dropped to almost zero, the density has dropped almost to zero, and you get to the solar system, outer space. Okay, now let's